So recording started. Just a couple of announcements quickly. I've moved the due date for homework number 1 back 1 day. So it was due tomorrow in my mailbox by 2 o'clock, but I moved it back 1 day to Friday at 2 p.m. in my mailbox. And that's just because I need a little bit more time to kind of cover the cranks and gears and things that I want to discuss. So give you a little bit more time. I won't have to rush through material. I was originally going to try to do 2 example problems today, but I'm only going to do 1 example problem today instead. Okay, so that's that. Another announcement is office hours. If you have homework questions, I've had a lot of people there kind of coming and asking questions. So again, every day, 9 a.m. to 10 a.m. And on Tuesdays and Thursdays, I also am there from 8 a.m. to 9 a.m. So if anybody's on the West Coast, my office hours are generally kind of early. So sorry if you move back to the West Coast and you have to get up early. If you really need accommodations, email me and we'll see what we can do. Okay. So before I kind of move, do we have any questions about homework? I did upload the new homework document containing the new due date to Blackboard. Also, the homework problem number 3 had sort of an incorrect answer and has now been updated accordingly. Okay. So if there's no questions, it doesn't look like there's any questions. We'll go ahead and just get started. So what I want to do today is just kind of want to review a little bit of what we talked about at the end of last lecture, and that is talking about general plane motion. So remember, we were discussing about the 3 types of plane motion, and that is translation, which is just all points having the same following along parallel paths. We had fixed axis rotation, where we're sort of fixed in space and rotating around one particular point. And then finally, we got to general plane motion, which is sort of a combination of both the translational motion and fixed axis rotation. David asks, is everybody else's audio working? So can everybody hear me? Let's just get some thumbs up in the chat if people can hear me. Okay, good. Everyone seems like they can hear me. So, wow, explosion. So David, it looks like you might be out of luck, buddy. Yeah, so audio seems to be working fine. Maybe you should press that mute button and unmute your audio. Okay, cool. Thanks. Glad everyone can see that. So we were talking about general plane motion, which would be a combination of both translation, moving from one space to another space, and then fixed axis rotation, which was rotating the system to get into the position that would be its final configuration. So I sort of attempted to draw this a little bit half-heartedly on my whiteboard yesterday, but I think it might be nice to actually pull up the PowerPoint to actually show the image that I was attempting to draw yesterday. It might clear things up just a little bit. So I'm going to pull up my screen here. And now you guys should all be able to see the PowerPoint lecture notes. These are the same lecture notes that are available on Blackboard if you kind of want to follow along. But at the end of the lecture last time, we were talking about this general plane motion, where we had, I like this image here on the bottom that really kind of displays and shows this pretty clearly. The relative motion of 2 different points on an object can be thought of as the motion of object number 1 in translation, or point number 1. Here we think about this point A1 moving to A2 by translation, and then point here B1 following that same translational path as A1, and then rotating about this point here A2 with a fixed axis rotation to get into location B2. So this is how we think about general plane motion being a combination of both translation and fixed axis rotation. Though we know objects might not necessarily have moved in that way. I think it's pretty rare to see an object actually translate and then rotate about some fixed point to get into position, but you might consider that mathematically as how that motion generally occurred. So when we think about that mathematically, we would say then that the velocity of point B, which is this arbitrary point in space, is the translational velocity that point A had, which is the translational velocity of point A, plus the velocity that B had relative to point A, which for us is like that fixed axis rotational motion of point B about A. And so that is sort of this secondary motion of B rotating about point A after the translational motion had occurred. So this is sort of how we want to visualize the relative velocities of 2 different points on an object in relation to each other during general plane motion of an object. Another a series of pictures that I'm just going to show here in PowerPoint that is probably better than what I could probably draw on the writing pad at this point. Demonstrates the relative velocity idea, again, what I think very clearly. So down here, I'm sort of talking about these particular images where we have general plane motion with two different points on the body. And these two different points could have completely different velocities since we're no longer translating or no longer do we have just strictly fixed axis rotation. We have general motion. So any point on the body could have any velocity in sort of any random direction. And we want to think about the total plane motion as a combination of both the translational motion. Here we're translating both points with the translational velocity of A, plus the velocity associated with the fixed axis rotation of B about point A. So if we say then we have a translational motion here, plus we're rotating about A with an angular velocity omega in k hat, creating a velocity at point B, which is tangential to what would be the circular path of B around A, kind of this circular motion, creating this particular velocity B with respect to A. So then the total velocity of point B, which is this vector here, is the translational component, the velocity of A, plus the fixed axis rotational component, the velocity of B relative to A, giving us our total velocity of point B. And so we can write the relative velocities of these particular points. Let's say the relative velocity of B is the velocity of A, which let's assume we know, plus the angular velocity of A crossed with the position vector locating B from A, which we know is the expression for fixed axis rotation. Okay, so it's like the translational velocity of A plus the velocity of B relative to A, which can be thought of as the fixed axis rotational component of the velocity of B with respect to A. So generally, this is the expression that relates the velocities of two different points on an object. And I'm telling you right now, you're going to write this equation 100 times. Okay, so really got to get this one burned in. All right, the relative velocity equation for 2 points on a rigid body. All right. So let's continue on here with maybe 1 or 2 more slides, and then we'll do an example problem to sort of round out the class for today. Maybe get you home a little early today. See what I did there? Because you're already at home. Okay, right. So when we think about this plane motion, let's consider a situation where we might have a rigid body, which is this sort of metallic rod here, connected to sliders at points A and B on either end. Now we can consider the rigid body motion as like the motion of this slider being the translation plus fixed axis rotation in one way, or we could think of it as like translation down and fixed axis rotation about the other point. So the idea is that we could have the general plane motion here being represented as, let's say, translation of B with A, and then rotation of B about A to get into position. Okay, so starting here and then rotating down to get into the final position that the slider has. Or we could think about this entire linkage as moving with a translational velocity of B. That is, A moves down with the same velocity as B, and then A has to rotate up to get into its final position here. So we could think about this rigid body motion as translation of point B and then rotation about B to get into position, or translation of A and rotation about A to get into final position. We could mathematically express that with 2 different relative velocity equations. Here in equation number 1, we have the velocity of B, which is the velocity of sort of this point here on the structure, this particular portion of the slider, is the velocity of A, that's this translational component, plus the fixed axis rotation of B about A. And we know that we have an angular velocity about A crossed with the position vector locating B from A. Okay, this is the expression that we have for a fixed axis rotation. Okay, similarly, if we talk about the velocity of A being the translational velocity of B, that is this velocity down, plus the fixed axis rotation of A about point B to get into position, that's sort of this motion here with point A sliding into its final position, we could express it using this general equation, which is the translational velocity of B plus the fixed axis rotation of point A about point B. So both of these equations would get us to an expression that gives us the velocities of these points equivalently. Okay, so in both situations, the object has arrived successfully in its final location, but we've mathematically thought about it in two different ways. One where the translation occurs with A and rotating about A to get into position. The other is translation with B and rotating about B to get into position. So generally, we have equivalent situations here. So we might think about plugging one equation into the other to see if we can learn some information about, let's say, the angular velocities or the velocities generally in this particular situation. Okay, so let's go ahead and take a look at what happens if we look at equation 1 here in equation 2 and plug one into the other. So let's make a note here about angular velocity by plugging equation 2 into equation 1. So equation 2 here is the expression for the velocity at point A in terms of the translational velocity of B and the fixed axis rotation of A about B. So we're going to plug this VA here into this portion of equation 1. So when we do that, this is the result. Okay, so we're looking now here at what is equation 1, but we have plugged equation 2, which is here highlighted by this gray, into equation number 1. So when we do that, we can simplify things. All right, meaning that the velocity B here on the right-hand side, the velocity B on the left-hand side, those things are going to cancel. Okay, so these guys will cancel out. I'm also then going to move this particular portion of the expression to the left-hand side of the equation. So we just put a negative sign in front of that. We've now moved to the left-hand side. So we rearrange, and this is our ultimate expression. I can distribute this negative sign in, and we'll note here that the position vector of B locating A is equal to the negative position vector of A locating B. So hopefully this sort of makes sense to you guys, but if we have 2 points in space, let's say point A is down here and point B is up here, a position vector that locates B from A is the same as the negative position vector that locates A from B. Okay, so hopefully we understand this general idea. If we plug that into this expression, we're left with this general equation here. So what this equation is more or less telling us is that in order for this expression to hold true, the angular velocity about point B must be equal to the angular velocity about point A, since the rest of this expression is the same. Okay? So generally, we would say that this equation is only true if the angular velocity about B is equal to the angular velocity about A for the two different situations we described. Okay? So what we might say in English is that the angular velocity of a rigid body in plane motion is independent of the point that you select. Okay? So if I'm moving generally in space with my rigid body, and I find the angular velocity at any point in time on that body at any point, that angular velocity is the same at all points on the body. Okay? So that really helps us with some of our angular velocity and relative velocity problems. Okay? So I'm going to pop back into chat here for just a second. Anybody got any questions thus far? No questions thus far. Have you tried turning it off and turning it back on? That's always a good thing. That's what I do with my OneNote here when it doesn't work. So good suggestion, Caleb. All right. So with that in mind, let's do a relative velocity problem. So I'm going to move this guy out of the way. And here we have a relative velocity problem where we're looking at a rigid body, which is this link ABD. So collars A and B are pin connected to ABD. So here we have pin connections of these collars, one at A, one at B. And they can slide freely along these particular directions. So we want to know, at the instant shown, the velocity of A being 0.9 meters per second to the right. So that's this point here, moving 0.9 meters per second to the right. We want to determine the velocity of this particular point. This is the velocity of point B. We want to determine the angular velocity of this particular rod. This is rod ABD. And remember that if we find the angular velocity at one particular point, we found the angular velocity of all points on the body. and we also want to find the velocity of point D. So I'll give you guys maybe 30 seconds or so. I know some of you are taking notes by hand. I'll give you maybe 30 seconds or a minute to sort of copy down this problem, and I'm going to translate this picture that you have on this slide onto my little whiteboard pad here, and then we'll work through the example problem on my whiteboard. Okay, so I'll give you maybe 60 seconds or so to sort of do that. Okay, so I'm going to stop sharing the PowerPoint now, and I'm going to move to the electronic writing pad. Got to be more precise with my vocabulary. The electronic writing pad. Someone muted me. Why do you mute me? Am I really that bad? Okay, so we should all be able to see the writing pad now, and I've kind of translated the information from the problem statement onto the writing pad. Okay, so you should be able to see the image here on the right-hand side of the link slider setup that we've got, and I translated the information from the problem, namely that we were given this velocity of point A is 0.9 meters per second to the right. So I've written that as the velocity vector A is 0.9 meters per second in I hat. So if I write this in I hat, I better put some coordinate system here for reference. So here's XY. I think that's generally intuitive, but let's make it perfectly clear. So the velocity of point A is 0.9 meters per second in I hat, and we're asked to find the velocity here of B. We're asked to find the angular velocity of the rigid body ABD, and we're asked to find the velocity of point D, which is out here kind of on the end. Okay. So let's go through that. The first thing that we want to do is understand that this is a relative velocity problem. Okay, we're given information about the velocity of point A, and we want to relate that information to the velocity of other points on the body, namely point B and point D. So in order to do that, we need to use our relative velocity equations. So here we'll use relative velocity equations. And the first thing that we want to do is we'll relate, let's say, the velocity of point A to the velocity of point B. So the way that we do that is we'll say that we're looking for the velocity of point B. And that's going to be equal to the velocity of point A plus the velocity of point B relative to point A. Okay? Or if we sort of expand this out, knowing that this is sort of the fixed axis rotational component, we could say that the velocity of point B is the velocity of point A plus the angular velocity of our rigid body ABD crossed with the position vector locating B from A. Okay? And this is just an expansion of our relative velocity equations. All right, so we've got a couple things that we need to define here. So a couple things that we can just look at straight away is VB we do not know, so I'll put a question mark there. That's something that we're looking for. The velocity of A we do know, so I'll give that a little red check mark. The angular velocity ABD, we don't know, so that's something that we're going to need to solve for. And the position vector locating B from A, that is something that we can obtain from the information given in the problem. All right, so it looks like we kind of have a few unknowns here, velocity of B and angular velocity ABD. But remember that the vector equations that we set up here are multiple equations. We have an equation in I, we have an equation in J. So we should have two equations available here for us to work with, given it's only sort of one equation that I've actually written on the paper. Okay, so let's define some of the things that we know straight away. First, we know that the velocity of point A is 0.9 I hat meters per second. All right, that's a good thing to know. All right, let's define. We know the angular velocity, ABD. Since we're rotating this rigid body in the plane, we know that the angular velocity vector is going to be restricted to the third dimension. Because we're rotating this guy in this two-dimensional plane, the angular velocity vector is going to be sticking out in just the third dimension. So I'll write the angular velocity vector as the scalar ABD, whatever the magnitude of the angular velocity is, and we know that this will be restricted to the third dimension here. This is k hat. This is strictly because we have planar motion, and we know that if we're rotating in the plane, that our angular velocity vector is going to be sticking out of that particular plane. Okay. Another thing we know is we can define the position vector that locates B from A. All right, so let's go back up here and we'll define that. So if we look at our picture, we have a position vector locating B from A, or if you want to think about the position vector arriving at B from A, that's going to look something like this. So here is the vector, position vector that arrives at B from A. All right, and we're given some information in the problem about the geometry. So we know here that this length from A to B is a total length of 300 millimeters. And here we have the angle that is formed between the vertical and the link itself is 60 degrees. Okay, so we can use that information to define the position vector that locates B from A. And specifically, we'll say that this is 300 millimeters multiplied by sort of the trigonometric relationships that we have in either one of the directions. This will be sine 60 I hat plus cosine 60 j hat. If we work this out and we convert to meters, since our velocity of A is given in meters per second, let's work in meters in this particular problem. So we'll convert the millimeters to meters and we'll use our trigonometric relationships here. And we'll have that the position vector of B relative to A is 0.26 I hat plus 0.15 j hat meters. Okay, so these are some things that we can sort of define straight away. All right, this helps us quite a bit. One other thing that we're going to have to consider in this particular problem is the condition of restriction on the velocity of point B. So notice here that the slider B is restricted to moving along this particular red line that I've drawn. So VB restricted to this motion. Okay, so just like the velocity of point A is restricted to only moving in the I hat direction, the velocity of B is restricted to moving along this particular line. Okay, so we might express that mathematically by saying something like VB is restricted to moving along a path. And we can express this mathematically as the velocity of B is equal to the magnitude of the velocity of B, whatever that magnitude is. We currently don't know what it is, but we know that the velocity is restricted to a path defined by that line, and that line is given by the unit vector that is, using the angular relationships that we have in the particular problem, cosine 60 degrees I hat plus sine 60 degrees j hat. So this is the unit vector here. Which VB is forced upon. So this is the line upon which VB must move. And we're going to move that particular piece along that line. So it's restricted to moving along this particular unit vector, which is defined by cosine 60 I hat, sine 60 j hat. We know that the components of the velocity of B will be restricted to those general directions. Okay, so this also sort of helps us define the problem. All right, so now we're actually ready to start plugging things in. So now we execute. Order 6-6. No, I'm just kidding, that's a Star Wars reference. Okay, now execute. And remember, our general equation is the velocity of B is the velocity of A plus the angular velocity of our piece AB crossed with the position vector locating B from A. That's the equation that we're generally executing. All right. So let's plug a bunch of this stuff in. We know that the velocity of B is the magnitude of the velocity of B restricted to the unit vector along which that particular velocity must act. And so that is cosine 60 I hat plus sine 60 j hat. And this is going to be equal to the velocity of point A, which we were given in the beginning of the problem, 0.9 I hat meters per second. That's the velocity of point A. Plus, I'll give myself a little extra space here, the angular velocity vector omega AB, which we were just calling omega AB, restricted to rotating in k hat. So this is the angular velocity omega AB k hat. We're going to cross this with the position vector locating B from A, which we previously defined as 0.26 I hat plus 0.15 j hat meters. Okay, so this is the general setup for my problem. Notice that this equation, which is actually two equations, one in I, one in J, has two unknowns. That's the magnitude of the velocity of B and the angular velocity magnitude, omega AB. So here we have, my pen ran out of ink again. Have you tried turning it off and turning it back on, as Caleb suggested? Okay, so two unknowns. That is the magnitude of the velocity of B and the magnitude of our angular velocity, omega AB, and we have two equations. One in I hat and one in J hat. Okay, so two equations, two unknowns. Let's go to town. We've been doing this since 6th grade. 6th grade? When do you start solving simultaneous equations? 7th grade? I don't know. I don't know math when you learn math these days. All right, so let's start in I hat. So we're just going to look at the I hat components here. So that's basically this guy here and this guy here and the I component resulting from this cross product. Okay, so let's write those particular pieces. Come on, baby. Need some space. All right. So that is the magnitude of the velocity of B, cosine 60 degrees I hat, equal to 0.9 meters per second. And if you execute this cross product up here, you'll get the I component being some k cross some j. So k cross j gets me negative I. So I'll have a negative 0.15 omega AB. So minus 0.15 omega AB. Okay. So here I have one equation and two unknowns. So let's rearrange this equation to solve for one of the variables. You can choose to solve for whichever one you want. Let's solve for the magnitude of the velocity. So if you rearrange this, you'll get the magnitude of the velocity of B after executing some math here is going to be 0.9 minus 0.15 omega on cosine 60. Okay, so here is equation star. I've just rearranged to solve for the magnitude of the velocity of B. So that's equation number one. And now I'll look in the J direction. And in J, we have very similar magnitude of the velocity of B. But here now our J component of velocity of B is sine 60 equal to, we have no component of the velocity in A in the J direction. The only thing that comes in the J direction from this equation is what happens when I cross K and I. So crossing K and I will give me a positive J. And so I'll have a 0.26 omega AB positive J from this cross product. So this is 0.26 omega AB. All right. So I can take what I solved for previously, this VB, plug it in down here. So here we'll plug in what we got from star. And we're just solving simultaneous equations here. And you'll end up with, after some algebra, omega AB is equal to 3 radians per second. That is the magnitude of my angular velocity vector. Okay? We can then plug back into star to get the magnitude of the velocity of B. To get the magnitude of the velocity of B, which here would be 0.9 minus 0.15 times the angular velocity magnitude that I just found is 3, all over cosine 60, or I'll be left with the magnitude of the velocity of B here is equal to 0.90 meters per second. All right. Now, I have found the magnitudes of the velocity vector and the magnitude of the angular velocity vector, but I have not actually found the vectors themselves. So in order to write the vectors appropriately, so to report these vectors appropriately, I actually need to write them as vectors, not as magnitudes. So my angular velocity vector for piece AB or ABD or BD or whatever, they're all the same, is the magnitude of this angular velocity, which we found as 3 radians per second. So that's 3 radians per second, and this acts in k hat. All right. So this is actually a vector because we have both magnitude and direction. And then also, my velocity of B is the magnitude of the velocity of B restricted to the unit vector along which it acts, which we know is cosine 60i. Sorry about the handwriting. Plus sine 60j. Or if you do this, generally the velocity at point B is, did I write this down? Yes, I did. Good job, me. 0.45 I hat plus 0.78 j hat, and this will be meters per second. Okay, so now we've defined magnitude and direction for our velocity vector. All right, so here now we've defined the angular velocity vector and the velocity at point B appropriately using vector notation. All right, so we'll take a little, I'm going to take a little pause here to look at the chat. Do we have any questions in the chat? No questions. Wow, you guys awake? Dang. I need some donations for my stream. Let's go. No, I'm just kidding. No donations. I'll get in trouble for that. Okay, so we still haven't quite finished yet. We figured out the velocity of point B, the angular velocity of our particular piece, but we still have to determine the velocity of point D. Okay, so still need velocity of point D. Okay, so let's go back up to our picture again, sort of remind ourselves where we are in this problem. Is that here we have this linkage. We've done the point up to this so far. We've determined the angular velocity of our rigid body, and we have determined the velocity of point B using relative velocity equations. So we're again going to leverage relative velocity equations to determine the velocity of point D. So here we're interested in also the velocity of point D, which is over here, which will have some velocity we don't necessarily know. And unlike point B, point D is not restricted by this sliding collar, okay? So we don't have an additional restriction here on D that defines the unit vector along which it acts. It can act, as far as we're concerned, in any general direction that it wants to, okay? So we're again going to use relative velocity equations relating the velocity of point A to the velocity of point D to solve this problem. You could also relate the velocity of point B, which we've now found, to the velocity of point D as well, but I think it's easier to relate the velocity of A to D because we know A is restricted in just one direction. Okay, so still need the velocity of D, and again we'll use relative velocity equations. Okay, so let's again write our general relative velocity equation, which is that the velocity of point D is the translational velocity of point A plus the fixed axis rotation component of D about A, which we know is the angular velocity omega AB or omega AD or omega BD or whatever, crossed with the position vector locating D from A. Right? Or arriving at D from A, or however you want to think about it. Okie dokie. So now away we go. Most of these things we already know. So let's do it. The velocity of D is the velocity of A we were given in the beginning of the problem, 0.9 meters per second in I hat, plus the angular velocity omega AB, which we know from before is 3 k hat radians per second, crossed with the position vector now locating D from A. All right, so we go back up to our problem here. We want the position vector locating D from A, so we want this position vector here, position vector locating D from A. All right, if we take a look at this, this is going to be something like 600 times sine 60 I hat plus cosine 60 J hat. Okay, that's just from trigonometry in the problem. All right, so we actually put this in directly. I'm going to convert to meters. So this is 0.6 times sine 60 I hat plus 0.6 cosine 60 J hat meters. All right, so this is the general setup for our problem. So we're looking for the velocity vector D, and that is our only unknown currently, and everything else is accounted for. So away we go. So here we have 0.9 meters per second I hat plus the resultant of this cross product here, which will be negative 0.9 I hat. So this is what happens when I cross the k component with the j component. Negative 0.9 I hat plus 1.56 j hat, and this will be meters per second. All right. So again, this is the translational component. So that is sort of how D slides along with A as it's moving. And this here is the fixed axis rotation component. And so that is how D slides down relative to A, right? Or how it moves relative to A. Right? So when we sort of combine terms here, we're going to end up with the velocity at point D is only actually moving in the y direction, or the j direction, and it's 1.56 j hat meters per second. Already in vector form. Very convenient, as we have noted. Okay. So that's it. All I wanted to cover today. Any questions on this particular problem? Okay. If not, that's it for today. Feel free to take off. I'll stick around for a couple of minutes if anyone has like homework questions or wants to talk about something else. And I'm going to stop the recording now. Okay. Thank you for coming.